Hey, Una. All right. So I was planning on saying more things about counting and probability because that's what we're doing now. It's all chapter 12 pretty much for the rest of the quarter. I should ask either you or what's your name? Sorry, say that one more time. Mamiasi? Mamias. Cool. Mamias. Mamias. So Una, Mamias, I should ask both of you, is there anything you want me to talk about specifically? It's totally fine if there isn't. But like if you have something that's like my teacher said this and I'm not really sure what that means or anything like that, I'm happy to offer some clarification. Okay. Sure. Well, certainly if I say something along the way that makes you think of something, let me know. Welcome, Swati. So yeah. Anyway, we'll continue on. So we did do stuff on Tuesday. If you haven't seen the class from Tuesday, you should definitely check it out. But let's go ahead and continue on with some examples. So we're still kind of just talking about how to count things. Most of section 12, chapter 12, I should say, is about counting stuff and then kind of about the number of ways you can maybe organize things. Just a few highlights from last time. What did I say? We talked about permutations, where again, when you hear the word permutation, you should think order matters. We distinguish between how like first, second, and third versus third, second, first, that kind of stuff. So we definitely are considering how our arrangement looks. Whereas combinations is just the number of way we can like take so many people from a group of so many. So we don't really care what order they're in. So typically the thing I would continue to think about is when you're talking permutations, usually the idea is that order matters. When we're thinking combinations, typically order does not matter. Those are the kind of the big picture things I think of when I think of those. Well, let's look at an example. Let's say, and let me get some, I got some pens here. Yeah, pens. Red, blue. Yeah. Let's say we have a jar. And it has or contains, what have we got here? 5 blue, 3 red, and oh, sorry, I got my numbers backwards. Sure, 4 and 4 black marbles. And we randomly choose 3. From the jar. So maybe you're thinking like, here's our jar. And we've got 4 black marbles. We've got 3 red marbles. My blue and my black maybe look too similar. Oh well. We've got 5 blue marbles. Yeah, blue and black, maybe not a great choice, but oh well. Such is life. 5 blue, 3 red, 4 black. So we're gonna pick marbles out here, and then I'm gonna remind you, it definitely feels like order is not important. I'm not asking like, how am I gonna get like a red, then a blue, then a black? I'm just gonna ask a question like, what's the probability of them all being blue? So, or I should ask, sorry, not probability. How many ways can we get all blue? It might feel like a weird question at first because you might be thinking, well, there's only one way. That's not the right answer, but you might think there's only one way because they all have to be blue. But the thing is, there's technically, and again, my colors here, not the best. There's technically 5. I'll make the blue marbles bigger. There's 1, 2, 3, 4, 5 blue marbles. So I could select these 3, but maybe I picked those 3, maybe I picked those 3, right? I could have picked any 3 of those 5. So the thing is, the number of ways we can get all blue is 5, choose 3, which I would encourage you to write like this. That's the usual standard notation for the choose function, unless your professor is doing something different. Has he talked about this in class yet? Let me before you answer that question, let me ask you: when you do 5 choose 3, it should equal 5 factorial over 3 factorial. Oops, that's a 3 times 5 minus 2 factorial. Is that sorry? 5 minus 3. Holy smokes, James. Sorry. Does that look familiar? Does this notation look familiar? Sure. Some other people write it like this, 5C3, or like this, C53. I prefer this notation. This is pretty standard for math people. But either way that you write it, the calculation is still the same. It's going to be 5 factorial over 3 factorial times 2 factorial, which ends up equaling 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. And I'll say the same thing I said about factorials as I said last time. When you're calculating these, if they're relatively small, you should probably simplify them. This one's pretty easy to simplify. We can cancel a 3, a 2, a 1, and then we have 5 times 4 on top over 2 times 1 on the bottom, which ends up being 10. On the other hand, later on, we start talking about cards specifically. If you're trying to simplify something like 52 choose 5, because we are often trying to simplify something like 52 choose 5, we just leave it as 52 choose 5 because the number is gross, right? It's like 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times, right? It's too big to really deal with. Speaking of which, since you're here in person, I have a handout. Here's a handout of some various terminology that we can use. If you've never seen cards before, or if you've never played with them much or talked about poker, there's all the poker hands. On the other side, there's some biology stuff. So if you come to class in person, I can hand you this lovely, lovely handout. Looks like this. It's in color. So, looks like this. Anyway. So, or you can come in my office sometime and get one if you really want, or print it out yourself. So let's continue on. What's the probability of them all being red? So, or sorry, I keep using the word probability, and that's kind of I don't want to say my bad, just that we often end up talking about probability. So if I were to just to kind of look towards the future here, I'll say a couple things. Thing one, I will say I want to find the number of ways, not the probability. Number of ways to get all red. Well, in this case, there is only one way, because if I'm selecting 3 balls, there are only 3 red ones. So there's only one way I can pick all 3 red balls. Or in other words, from the 3 red balls that there are, I want to choose 3 of them. And it's worth knowing that whenever you have a number choose the same number, you're just saying, how many ways can I pick 3 things out of 3 things? Well, there's only one way. I pick all 3 of them. Now, actually, we should calculate this because I want to remind you of something I said on Tuesday. If I calculate this, look what we get. We get 3 factorial over 3 factorial times 3 minus 3 factorial, which ends up being 3 factorial over 3 factorial times 0 factorial. And if your teacher has hopefully said this in class, or if you're here last time, I definitely remind everybody that 0 factorial is defined to be equal to 1. So we're not dividing by 0 here, it's not a problem. We end up getting 3 factorial over 3 factorial, which is 6, times 1, which ends up just being 1. So whenever you're trying to pick all the things out of however many things you've got, there's only one way of doing it. You pick them all. So in general, just as an aside here, n choose n is always equal to 1. Because there's only one way of picking all n things out of n things. And just to go along with that, because it's useful, n choose 0 is also equal to 1. And though it sounds weird, right? If I had like 3 red balls and I said how many ways are there of picking 0 of them, well, there's one way. I don't pick it. Well, that's actually not a good example here. Sorry. If I have n things and I'm trying to pick 0 of them, there's only one way I can pick 0 of them by not picking any of them. Again, this is not maybe the best venue for that particular thing, but when you're choosing 0 things out of n things, there's only one way you can choose 0 of them, which feels kind of weird. You're like, I'm not picking anything, but okay. There's something else here. Oh, back to what I was saying before. So the reason I keep saying the word probability is because that's where we're eventually going. So if I wanted to ask what's the probability of picking 3 red balls, well, then I would find the total number of ways of picking 3 red balls, which is 1 out of the total number of ways I could pick any 3 balls. So even though we're not going there yet, I would just point out that there are, well, let's see, there's 5 plus 3 plus 4, which is 12. There are 12 balls total. And there are 12 choose 3 ways of picking any 3 balls. Right? There's 12 total, and I just want to pick 3 of them. There's 12 choose 3 ways I can do that. And calculating this would be 12 factorial over 3 factorial times 9 factorial. Whenever I look at a calculation like this, I'm thinking 12 factorial over 9 factorial, most of that canceling out. I know that 12 factorial is 12 times 11 times 10 times 9 times all the way down to 1. And 9 factorial is 9 times 8 times all the way down to 1. And the 9 down onward is going to cancel. So when I write this out, I don't usually like to write 12 times 11 times 10 times all of this. It just becomes kind of tedious. And on the bottom, I've got 3 factorial. And then 9 factorial, which is the 9 times 8 times 7 times. And I'm seeing that, oh, the 9s cancel, the 8s cancel, everything after 9 cancels. So I'm left with 12 times 11 times 10 over 3 times 2 times 1, which is 6. 12 divided by 6 is 2. 11 times 10 is 110 times 2 is 220. So what I would say here is that the probability of picking all 3 balls red is 1 out of 220. Because there's one way of getting the thing we're talking about getting out of 220 possible outcomes. In a similar way, if I said what's the probability of picking all the balls to be blue, the probability would be 10 out of 220, because there are 10 ways of getting what you want out of 220 ways of getting anything. And that's generally the idea of probability is if you're trying to find the probability of something happening, it is the number of ways that thing can happen divided by the total number of things that can happen. It's a good thing to remember. In fact, I should write that down. Oh, I don't know. So let's continue with this marble example. And I'll try to keep using the language I mean to use, which is, let's see here, how many ways could we select one ball of each color? So 1 red, 1 black, and 1 blue. Well, if I want just 1 blue, there are 5 different balls I could pick. So my 1 blue is going to be 5 choose 1. And there are 3 red balls, so there's 3 choose 1 ways I can pick a red ball. And there are 4 black balls, so there are 4 choose 1 ways I can pick 1 black ball. Now, I will point out this calculation comes up often enough that you want to know what it is just without doing all the work. So yeah, we could totally find 5 choose 1. 5 choose 1 is equal to 5 factorial over 1 factorial times 4 factorial. What's that going to end up being? Let's take a look. Right, exactly, just 5. If we think about the words we're using, 5 choose 1, it totally makes sense that would be 5, because you're saying, how many ways can I pick one thing out of 5 things? Well, I can either pick the first one, or the second one, or the third one, or the fourth one, or the fifth one. And there's 1, 2, 3, 4, 5 different ways I can make that selection. But we can also do the calculation. And 1 factorial is 1, and 4 factorial is 4 times 3 times 2 times 1, and those all cancel. That's exactly 5. In the same sort of way, 3 choose 1 is 3, and 4 choose 1 is 4. And so we get 5 times 3 times 4, which is something, 60. So there are 60 different possible ways I could pick 1 red, 1 blue, and 1 black ball. And again, I think I should make a note here. In general, it is true that n choose 1 is equal to n. If you're trying to pick one thing out of n things, you're going to get n ways of doing it. It's also worth noting that n choose n minus 1 is also equal to n. So let me actually phrase this kind of differently. Just for example, what if I wanted to find 20 choose 19? I'm asking how many ways can I pick 19 things out of 20 things? That might feel like kind of a hard question to answer, but it's not if you view it in a different way. So instead of asking how many ways can I pick 19 things out of 20 things, the question I really want to ask is how many ways can I exclude one thing and pick the other 19 from 20 things? Well, I can either exclude the first thing and pick the other 19, or the second thing, pick the other 19, or the third thing, or the fourth thing, or right? So on and so on. So this ends up being just 20 because there's 20 different ways I can take one of the things out. So sometimes it's more sensible to think about what you don't want instead of what you do want. But really, the kind of idea here is that when these bottom parts are add up to n, their choose function ends up equaling the same value. So it's true that, just like I said on the previous page, it's true that n choose 0 equals 1. It's also true that n choose n equals 1. And more generally, it is true that n choose k is equal to n choose n minus k. For example, 5 choose 2 is equal to 5 choose 3. And they're both equal to 10. The number of ways of picking 2 things out of 5 or the number of ways of picking 3 things out of 5 end up being the same. Because the number of ways of picking 2 things out of 5, you say, oh, if I want to pick 3 out of 5, I'm just going to pick the 2 out of 5 and then pick the other 3 instead. It's kind of neat. Let's see. Let's make this a little more interesting. What if I wanted to pick my numbers are blue. 2 blue and sure, 1 black. So at this point, the idea is, I think, becoming relatively straightforward in that I want to pick 2 blue and 1 black. Well, there's 5 blue to pick from. So that's going to be 5 choose 2 times, well, if I want to pick 1 black, there's 4 choose 1 ways of doing that. And then I haven't said this, but we're totally using the multiplication principle here every time, right? We're saying, okay, I want 2 of these and 1 of those. So I'm going to multiply the possibilities together to get the total number of possibilities. This ends up being, let's see, 5 choose 2 is going to be, well, I wrote it over here, but I can show it. It's 5 factorial over 2 factorial times 3 factorial. But I should just say that 4 choose 1 is 4. And so then that's going to end up being 10 times 4, which is 40. Let's make the questions a little bit more interesting. What if instead I wanted to count the ways of getting no blue balls or marbles? Well, I forgot how many there were of each. Let's see, let's go back. There were 5 blue, 3 red, and 4 black. So if I want no blue, well, how many no blue balls are there? Well, there's 3 red and 4 black, so there are 7 balls I can choose from. And how many am I picking again? Right. So it's going to be 7 choose 3. And at this point, I might just choose to leave the answer like that. The assumption being that, yeah, we could do the calculation, right? It's not like we don't know how to do it. We could also calculate it. Something you should get used to seeing is when you do this choose calculation, the bottom 2 factorials should add up to the top number factorial. 3 plus 4 is 7. That doesn't mean the bottom is equal to the top. It just means that when you're calculating this, you should see that same pattern occur over and over and over again. Then when you calculate this, so just to make sure that everyone saw this, if you have a calculator, you probably have this button somewhere on your calculator. So I want to calculate 7, choose 3. Let's see. In a lot of calculators, it's going to be in the, where was it last time? I forgot. Is it in the probability stuff? Yeah, it is. So you're going to do 7, and then you're going to hit probability, choose NCR for the choose function, not NPR for the permutation function. Hit enter, and then 3, and then hit enter. And it'll give you the number, 35, which it totally is. Right? If you calculate this, 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, which is 6, and 4 factorial, which is that. And we exactly get 35. So yeah, you can totally, especially when they get bigger, you can totally use the calculator to calculate those things, and it's a good idea to do so. I think there are definitely questions that get asked that have bigger numbers involved, but typically when that happens, we usually just leave them as whatever the number is, like whatever the choose function is. So like, again, like I was saying, like if you're doing like 52 choose 5, we're usually not going to simplify that down to actual numbers. We're just going to leave it as 52 choose 5. Yeah. Let's say we wanted to do the following. Let's say we wanted to know what's the probability. Sorry, not the probability. I keep thinking probabilities. It's hard to get away from so much probability. So how many ways to select 3 marbles and get at least 1 blue marble? And this example is going to illustrate an important idea of you can count things different ways and get to the same result. So one way to do this would be to count up, well, if I want at least 1 blue marble, I can either have 1 blue marble or 2 blue marbles or all 3 blue marbles. And I can add those all together. So getting exactly 1 blue marble, well, there were again, right, there's 5 blue. I've actually forgotten what I said. 5 blue, 3 red, and 4 black. So if I want 1 blue, I'm going to do 5, choose 1. And then the other 2 balls are going to come from red or black. So that's going to be 7, choose 2. If I want 2 blue, that's going to be 5, choose 2. And the other 2 balls, the other 1 ball will come from the red or black one. So it'll be 7, choose 1. And finally, and this is actually going to show something as well, for 3 blue balls, I already know it's going to be 5, choose 3. You could even go a little bit further though and say it's 5, choose 3 because I want 3 out of the 5 blue balls. And I want 0 out of the 7 not blue balls, which is just not going to change anything because 7 choose 0 is equal to 1. So calculating this, here's what we've got. We add these all together. 5 choose 1 is 5. 7 choose 2 is, I guess we should calculate it. Fine, let's use the calculator. Do 7 choose 2. 7 choose 2. It should end up being 21. Yeah. Plus 5 choose 2, which we've seen a couple times, is 10. Times 7 choose 1, which is 7. Plus 5 choose 3, which is also 10. Times 7 choose 0, which is 1. And that ends up being, let's see, 105 plus 70 plus 10, which is 185. There's 185 ways of picking at least 1 blue ball. Now, that was kind of a lot of work. It was more work than we actually needed to do. Because here's another way of doing it. Instead of counting the number of ways of getting at least 1 blue ball, we can say the following. Well, the total number of ways to pick 3 balls. We already calculated, but I'll do it again. It was 12, choose 3. Because there were 12 balls total, we're picking 3 of them. And we calculated that to be 220. I'll show you on the calculator as well. If I do 12, choose 3. Just because it's fun. I like doing it. It is 220, like we said it was. Okay, now here's the thing. If you think about picking 3 balls, you only have a few different things that can happen as far as number of blue balls. You can either have 0 blue balls, or 1 blue ball, or 2 blue balls, or 3 blue balls. Right? One of those 4 things has to happen if you pick 3 balls out of this jar. And so all these things added together, the number of ways of getting 0 blue balls, the number of ways of getting 1 blue, the number of ways of getting 2 blue, the number of ways of getting 3 blue, that should add up to 220. And instead of actually calculating what all of these are added together, I could instead say, well, the number of ways of getting, to get the number of blue balls being greater than or equal to 1 is going to equal 220 minus the ways of getting 0 blue balls, which we just calculated, right? On the previous page, the way of getting no blue balls is have 35 ways of doing that. So calculating this, that's going to be 220 minus 35, which is exactly 185. Which in my mind is an easier calculation because we're doing less calculating. This is kind of what's called the idea of the complement, meaning basically if you add up all the things that can happen, it has to add up to all the different possibilities total. And so if you're trying to find the probability, or it's not probability, sorry, if you're trying to find the number of ways of getting all of these, you can say, well, instead of calculating all that, I can say what's the total number of things that can happen minus the number of things that I don't want to happen. And that's a very, very strong tactic that we use sometimes when we calculate stuff. It's not as obvious here that it's a much better way to do it, but like if instead of there being like only words here, let me think for a different example. I'm trying to think. If the number of balls was larger, like if I was picking 5 balls instead, and I wanted to know what's the number of ways of getting at least 1 ball, that'd be 1 ball plus 2 balls plus 3 balls plus 4 balls plus 5 balls. And I have to calculate all 5 of those things, or do this minus the 1 thing over there. So it's usually less calculation intensive. Yeah. Cool. Some more examples. All right. So let's see what I've got here. So UC Davis holds a conference. In which there are 20 undergraduates, 20 graduate students, 20 transfer students, and 20 international students, and 20 faculty. I should just use an F there. I don't know why I'm writing faculty out. And we're going to ask the following. So the first question is, how many committees of 10 undergraduate students, can we make? So if I want my committee to consist of just undergraduates, well, there are 20 undergraduates to pick from. I want to pick 10 of them. Order doesn't matter because I don't care if I pick you first or you first or you first or you first. As long as I get 10 people, I don't care which ones came onto the committee before the other ones. So we're going to get that to be 20 choose 10. And at this point, it's definitely probably just leave it like that. You could write, 20 factorial over 10 factorial times 10 factorial, but it's probably too much to calculate by hand. If you use the calculator, let's see what happens, just to kind of see what happens. Whoops, 10, 20 choose 10. That's a pretty big number. 184,756. So there are 184,756 different possible committees of 10 people we could make out of our 20 undergraduates. Interesting. Okay. So the second question here, which is going to be very similar to the first, is how many committees can I make that consist of 10 people who all have the same type of classification, meaning all undergraduates or all graduates or all transfer students or all international students or all faculty. So, well, we know how to do it with they're all undergraduate students. It's going to be 20 choose 10. And then if they're all graduate students, it's also going to be the same thing, 20 choose 10. And it's going to keep on being 20 choose 10 for all undergrad, grad, transfer, international, and faculty, which is really just 5 times 20 choose 10, which is how we should write our answer. And again, this work is really being done so that we can easily answer what our last question is going to be, which is the following. How many committees can we make of 10 people contain people from at least 2 different groups? Okay, now, this question is kind of terrible because I want to find the number of ways of getting people from at least 2 different groups. They can say, well, like there's a lot of ways I can do that. I could say I'm going to get 9 undergraduates and 1 graduate student. So that'd be 20 choose 9 times 20 choose 1. Or I could do 9 undergraduates and 1 transfer. Again, the same calculation. Or 9 of these and 1 of those, and 9 of these, 1 of those. But then I could do 8 of these and 1 of those and 1 of those. Or 8 of these and 1 of those, right? There's way too many things to actually count here. Right, 8 and 1 and 1, 8 and 1 and 1, 8 and 1 and 1, 8 and 1, like just even that, and then I can do 7 and 1 and 2, or 7 and 1 and 1 and 1, or right, there's just like a lot of ways you can count this. So this is definitely an example where instead of counting the things that you want, we're going to count the things that we don't want and subtract them from the total. So let's ask what the total is first. So the total number of ways we can make a group of 10, or to make a committee of 10. Well, in total, there are 100 people, 20 undergraduates, 20 graduate students, 20 transfer, 20 international, 20 faculty. So if I want to make a group of 10, there's 100 choose 10 ways of doing that. And not surprisingly, maybe, this thing we calculated up here is actually the thing that is all the stuff we don't want in this question. Because this answer up here is all the ways to make committees that have exactly 1 type of person from that group, but not more than 1 type of person, right? So, right, this is all undergraduate, this is all graduate, all transfer, all international, all faculty. And that is all the ways you can make a group that have just all undergraduates or all that or all that or all that. So now, if I'm trying to calculate the number of ways of getting at least 2 different groups of a thing, well, I don't want any of this, but anything else will be fine. I could have 9 of these and 1 of those, or 5 of these and 1 of those, and 2 of those, and 3 and 2 of those. So I'm going to subtract off. Actually, I should say, so what I want here is going to be exactly 100 choose 10 minus the thing I just calculated up there, which is something. I don't actually want to calculate it, but I would leave it like that. It's gross. Because again, the idea here that's coming into play is that, write this out here, right? Is that, sure, the number of ways of counting groups that are all from the same group plus the number of ways of counting people that are at least 2 different groups. And I should point out, these are wholly non-overlapping or disjoint from each other. You can't have both. There's not like a combination that meets both of these criteria at the same time. You either have people that are all from the same group, or you have people from at least 2 different groups, and there is no overlapping. And that also consists of everything, because one of those two things has to happen if you're picking 10 people. They're either all from the same group or they're not. It's kind of it. So this adds up to all possibilities, which is, in this particular case, are 100 choose 10. And this right here was the thing we calculated. 5 times 20 choose 10. And so this right here is the difference between that minus that. Again, this idea of the complement, where the two things that can happen have to add up to kind of everything. And so if you're trying to find one of them, you can do everything minus the other one. Ooh, nice. Let's see here. Yeah. What time is it? Oh, we got time. We got plenty of time. So I might feel like the examples are maybe a little repetitive, but they're good examples. It's good to kind of, there's a lot of different things you have to kind of think about. Excuse me. And sometimes it can feel kind of tricky to be like, oh, we're doing a thing that seems maybe somewhat, what's I'm looking for? Non-intuitive, but that's why we're practicing. So let's look at a few more examples here. Let's see. So let's look at this example here. How many ways can we form a group of three? Oh, sorry, apologies. From a group of, sorry, I didn't need that. Form, how many ways can we form 3 committees of 5 people each from a group of 15 if people are allowed to serve on multiple committees? Okay, so let's think about this here. Is order important? I don't think so. It doesn't seem important. It doesn't really matter which. So let's think about it. We've got committee 1, we've got committee 2, we've got committee 3. So for committee 1, there's 15 people to choose from, right? Because there's 15 people all together, and I want 5 people on this committee. So there are going to be 15 choose 5 ways of doing that. Now here's where we have to be careful. You might make the incorrect choice of saying, well, I used up 5 people, now I only have 10 people left, but we didn't, because people are allowed to choose to serve on multiple committees. So for our second committee, we're also going to have 15 choose 5 choices. And for our third committee, the same thing is also true, 15 choose 5. So here, our answer is, well, should we be multiplying these together or adding them together? That's a really good question. It's not always easy to know. So how do I say this the right way? I don't want this to be something you necessarily, I'm just trying to hedge here. Most of the time, when we use the word and, it usually indicates we have multiplication. In contrast, most of the time when we use the word or, it usually means you have addition. So what I'm thinking of here is I have this first committee and this second committee and this third committee. Right? It's not an or, it's not like I have this one or this one. I'm making all 3 committees. And you can serve James, myself, could serve on this committee and this committee and this committee if I wanted to. So we should have multiplication here, because really I want to find all the ways I can have one committee times all the ways I can have a second committee times all the ways I can have a third committee. This is really going to equal 15 choose 5 times 15 choose 5 times 15 choose 5. And it's multiplication. And yeah, that's a very, I should say, that's a very loose interpretation, right? Like it's not always 100% true. It's mostly usually true that when you talk about one thing and another thing needing to happen, that we multiply those numbers of ways of getting that together. Let me think. I should think of a better example. Yeah, let me think. I don't have anything else, but we'll come back to that. So you could leave this like this. I probably would. I guess if you really wanted to, you could write it as 15, choose 5 to the third power. But that seems like a weird thing to write, so I probably wouldn't do that. Okay. We could also have the situation where people cannot serve on multiple committees. So then for my first committee, I do still have 15, choose 5 different ways of making my first committee. But then after I've selected 5 people to be on my committee, those people are spoken for, right? They can't do anything else. So for the next committee, committee 2, I don't have as many people to choose from. I only have 10 people left to choose from. Still choosing 5. For my third committee, I only have 5 people left to choose from. So those 5 people have to be on that committee, right? There's no other choice. Meaning that last one's going to be 5, choose 5. And we know that 5, choose 5 is equal to what? Yeah, thanks. I appreciate the participation. Thank you. Feel like you don't have a choice. It's only me. You all could also chime in if you wanted. So this ends up just being, I would write this as 15, choose 5 times 10, choose 5. And it still is a multiplication because we're still saying we want to count the number of ways of getting the number of ways we can get this first committee times the number of ways you can get the second committee. Because, right, maybe we have, persons A, B, C, D, and E on this first committee and persons F, G, H, I, and J on the second committee, but maybe we want 5 other people. So we still want to have that first possibility kind of paired with every second possibility. So that's why we're multiplying all these possibilities by all of these possibilities. Kind of weird, but it definitely works out. Yeah, let's look at another example here. I think this next example is a little bit better at kind of embracing the multiplication idea. Let's say we have 5 textbooks and 6 novels. Okay. In how many ways can we place 3 of the textbooks and 2 of the novels on the shelf? Okay. So there's a lot of possible combinations here, right? So of the 3 textbooks, I'm going to choose 3 of them. Sorry, of the 5 textbooks, I'm going to choose 3 of them. So here's my number of textbooks. And of the 6 novels, I'm going to choose 2 of them. And I do want to really kind of, so let's just think about this for a second. Let's say my textbooks, let's say that they were numbered 1, 2, 3, 4, and 5. And my novels were lettered A, B, C, D, and E, and F. So let's say we pick 3 of the textbooks. Let's say we pick textbooks 1, 2, and 3. Then I want to find how many different ways I can get those paired with any 2 novels. So I can do 1, 2, 3 with A and B, or A and C, or A and D, or A and E, or A and F, or B and C, or B and D, or B and E, or B and F. I know it's a lot here, but we can write them all out. Or, sorry, brain. That'll be fine. Yeah. Or C and D, or C and E, or C and F, or D and E, or D and F, or E and F. Let's count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which is exactly what 6 choose 2 is equal to. 6 choose 2 is equal to 15. Now here's the idea. We're taking this one particular combination of 3 textbooks and multiplying it by all 15 ways we can pick 2 novels. But then we want to do that for every possible combination of 3 textbooks. So we'd also do that with Textbooks 1, 2, and 4 would go with all of those. Textbooks 1, 2, and 5 would go with all of those. So every possible combination of 3 textbooks needs to get multiplied by every possible combination of 2 novels. And that's why we're doing the multiplication, because we want 3 textbooks and 2 novels on the shelf. Now, I should point out, and I didn't write this because I was waiting, but we also want to, how many ways can we place 3 textbooks, 2 novels on the shelf? And we should point out that the arrangement matters. Because, what's that? Well, so it's kind of a mix of both things together. So we're certainly using the combinations to figure out the number of ways to pick 3 textbooks and the number of ways to pick 2 novels. But then after we picked our 5 books, let's say we picked books, 1, 2, and 5, and D and E, for example. Then we're going to take these 5 books and say, well, how many ways can you order them on the bookshelf? You could do 1, 2, 5, DE, or 1, 2, 5, ED, or 1, 2, E, 5D. And it goes on and on and on. I don't want to list them all out because there's 120 ways of doing it. But the thing here is that after we picked our 5 books in total that are going on the shelf, then we're going to multiply this by 5 factorial, the number of ways we can permute those 5 books that are going on the shelf. This ends up equaling 5 choose 3 is 10, 6 choose 2 is 15, which we calculated, and 5 factorial is 120. So whatever that ends up being. I think it's 18,000. Let's find out. Yeah, it should be. Yep, cool. So there are 18,000 ways of arranging 3 of my 5 textbooks and 2 of my 6 novels on my shelf. Seems like kind of a lot, right? Like you wouldn't maybe think of 11 books. There are 18,000 ways of picking precisely 3 of your textbooks and precisely 2 of your novels and putting them on the shelf. But yeah, there are. Okay, let's see. Let me look over here for a second. Yeah, I don't love these. We'll come back to that. So there are more questions we can ask. Should we get to the probability stuff? I feel like we're not quite there yet. Let's continue. Let's talk about more counting. So various professors go different directions. Some people really kind of focus on one style of question, some focus on another. I was looking at, where'd you go? I was looking at your homework assignment that got posted yesterday, and most of these questions seem moderately straightforward. Yeah. But there are some probability questions, so we should get to that at some point. We will certainly, if we don't today, we'll definitely get to it by Tuesday, which is the day before this is due. Right, yeah, because today's the 17th. Next Thursday is the 24th. Next Thursday is Thanksgiving. We don't have class next Thursday. The next Tuesday is the 22nd, and we definitely will meet then and we can cover more of this. But let's talk about a few more examples like the following. That pen. Okay, you've had your time, pen. Let's try you. How many distinct factors of the number 360 are there? That's a good question. Feels like it might be too challenging to just list them all, right? You could start, you say like, okay, 1, 2, 3, 4, 5, 6, not 7, I think 8, pretty sure 9, 10, 12, but right, the list goes on, right? Up to, like 180 and then 360. Those would be the last 2. How many of them are there actually? Well, here's a way you can always figure out how many distinct factors a number has. You have to do its prime factorization. So I'm just going to break 360 down until I can't anymore. So do whatever you like. I'm thinking the easiest way to break this up is 10 times 36. But really, whatever way you want to get there is fine. And then 10 is 2 times 5. 36 is 6 times 6. and each of those sixes is a 2 times 3. So I could write 360 as, let's see, I've got 2 times 2 times 2, so 2 to the third, and 3 times 3, so 3 to the second, and 5. So now all I have to do is think about how many of each of those factors I could have. So I could have either a 2 to the 0th, a 2 to the first, a 2 to the second, or a 2 to the third. Those are my only options for the power on 2 I'm allowed to have. And then I could have a 3 to the 0th, a 3 to the first, or a 3 to the second. And then I could have a 5 to the 0th or a 5 to the first. Let's just make a choice just to kind of see what happens if we choose. Let's say we picked 3. Oops, that's not what I wanted. Sorry. Let's say we picked 2 squared and 3 squared and 5 to the 0. Let's see. That gets me 2 squared times 3 squared times 5 to the 0 is 4 times 9 times 1, which is 36, which is definitely a factor. Right? No matter what you choose, if you choose one of these, one of these, and one of these, you're always going to get a factor of 360 because 360 is 2 to the third times 3 to the second times 5 to the first. So let's see what we've got. We have, for our choice of power of 2, we have power of 2. We have 4 choices. Our power of 3, we have 3 choices. And our power of 5, we have 2 choices. So it looks like 4 times 3 times 2, it looks like there are 24 distinct factors of 360, which I think is, I don't know, kind of neat. You could totally list them all out. Like, it's not impossible. We could keep going here. We've already listed 2, 4, 6, 8, 10, 12 of them. There's 12 more left. You could probably find them pretty easily, but I don't think we need to. So I don't think we should. Kind of want to do it though, but I don't really. Yeah, okay. Gotta stop myself before I try to do it. It's not important. So some other questions. So a lot of these questions are, right, like this isn't, I would say that like you don't often see a question like this. You might see one, you might not. But the idea here is that we have to kind of develop a way to make sure we are thinking about all the possibilities for whatever kind of situation we're encountering. Let's look at another example. So we're going to ask how many even numbers are there between 20,000 and 70,000 with distinct digits. Distinct meaning no repeats. So let's think about what our 5 digits of our number could be. And maybe I'll call them A, B, C, D. And then we're going to start trying to find some conditions on each of the numbers. Well, first and foremost, we've got a condition on A. Right? If we're between 20,000 and 70,000, you can either have A equal to 2, 3, 4, 5, or 6. I guess you could technically say 7, but we know that the one number that starts with 7 is going to be 70,000. So I don't think we really need to worry about that. No, we'll just be like, oh yeah, we know 70,000 is also a number. So we're going to break this up into a couple different things. Well, in fact, actually, I should say one more thing. We also have conditions on E. E, since the number has to be even, that wholly dictates that the number E has to be even. Everything else can be odd, right? A, B, C, D, and E can be odd or even, sorry, A, B, C, and D can be odd or even numbers, but E has to be either 0, 2, 4, 6, or 8. There are no other options for E. Okay, so now we kind of have to break this down into cases. So let's say case 1. Basically, we need to differentiate between where A is an odd and A is an even number. Because if A is even, then we're limited into what we can choose for E. So let's start with A being odd. So A is either 3 or 5. Okay. So if A is 3 or 5, we have two choices for the first thing. 3 or 5. And then I would look at my most restricted point next. So then for E, well, E we have 1, 2, 3, 4, 5 choices, right? Because we didn't pick any of those. We only picked either 3 or 5. So then all of these are left over to pick from. So E has 5 choices. So great. Now I've picked 2 of my numbers. And again, we are restricted here by the fact that we can't have any repeated digits. So I've picked, let's pretend we picked the number, we picked 3 and 8. So 3 and 8 are gone. Now we only have 0, 1, 2, 4, 5, 6, 7, and 9 to choose from. Or in other words, there are 8 choices left because we've used up 2 of our digits. So then in this spot, there are 8 choices. And then we used up another one. So in this spot, there are 7 choices. And in this spot, there are 6 choices. So here, the number of even numbers between 20,000 and 70,000 that start with either a 3 or a 5 are 2 times 8 times 7 times 6 times 5. Okay. Oh, sorry, I should point out 70,000 is not a number we need to include because 70,000 doesn't have distinct digits. So I should cross that out. That's not what we want. Read the question, James. So then case 2 is a little bit more dicey. A can be 2, 4, or 6. Okay. So then if A is 2, 4, or 6, we have 3 choices for the first digit, 2, 4, or 6. And then, well, if we've picked one of those even numbers, we have less choices for our last digits. If I pick 2, I can't pick 2 for my last digit, so there's only 4 choices for that last spot there. Which is why we need to break this up into cases so we can make it easier to deal with. And then we pick something here, we pick something here, so then we have 8 choices here, and 7 choices here, and 6 choices here. And these two numbers added together, so this ends up being 4,032. This ends up being 3,360. If we add those together, we get 7,392 total possible such numbers. Total possible even numbers between 20,000 and 70,000 with no repeated digits, with distinct digits. Again, the point here really not being so much to answer the question, but to think about how we break the question down into more digestible parts, right? Without kind of breaking this up into these 2 different cases here, it's hard to think about what that last digit can be since it has to be an even number. But if we break it into the case where A is odd versus A is even, then when A is even, we can see, oh, I've used up one of the even numbers there. So I only have less choices over here for the last one. So I made this choice first. Right, there were 2 possible choices. I could pick 3 or 5. And then I made this choice second. There were 5 possible choices: 0, 2, 4, 6, or 8. And then after I made those 2 choices, I used up 2 of my digits. And then for this spot here, there were 8 choices left. And then I made the choice there. And then for this spot there were 7. And then for this spot there were 6. So because I did this first, so I used up either 3 or 5. So I can't pick. So anyway, I was pretending like I picked 3, right? So I can't put the number 3 there. And then I made this choice next. This is my second thing I looked at because it has some restrictions. It's all right. Yeah. So well, I mean, I'm not like this could be 3 or 5, but I'm saying I picked 3, for example. This could be 8 or 6 or 4 or 2 or 0, but I picked 8. Or maybe no. yeah, let's say I picked 0 instead. And then after I've picked 3 and 0, well, there's only 8 choices left for this spot because they have to all be different. So if I pick 3 and 0, all that's left are 1, 2, 4, 5, 6, 7, 8, and 9. So from one of those 8 digits that are left, I'm going to pick one of them. So there are 8 choices there. And then after I pick one of them, there's 7 there, 6 there. Same kind of thing is true here. Here I'm picking 2, 4, or 6. And then here I'm picking whatever from whatever's left over. So let's pretend that I picked the number 2. And then here I'm left with, well, I can't pick 2 because it's already been picked. So I have to pick 8, 6, 4, or 0. So I can't pick the number 2. It's already been chosen. So I only have 4 choices there. Let's pretend I picked 0 again. And then after I've made those 2 choices, I'm back down to 8 choices left here, 7 choices left here, 6 choices left here. So that's what's going on there. That's a good question. Okay. Oh yeah, these are the things that are interesting. Suppose my pens. I've ordered new pens, they just haven't come yet. Promise you, I'm gonna have pens that write better soon. Suppose we have 5 girls and 4 boys, and they're going to be seated on a bench. How many ways can they be arranged? So if there's no restrictions, well, there's 9 factors. So again, I should point out here that we're making the assumption that each girl is a different person, right? It's not like we have 5 identical twins or clones of each other, right? We have 5 different girls, we have 4 different boys. And so if, girl A and girl B switch seats, that is considered a different order. So if we have no restrictions on who sits next to who, then we're just going to get 9 factorial possible arrangements because there are 1, 2, 3, 4, 5, 6, 7, 8, 9 seats on our bench, and we have 9 choices for the first spot: 8, 7, 6, 5, 4, 3, 2, 1. But again, when you're talking about seating people next to each other, we're usually in an order matters situation because we consider all the people to be different people. You could maybe say things like we don't actually care which boys sit next to each other as long as they're boys, but we haven't said that here. So let's look at a more restrictive seating. Let's say we want all the girls must sit next to each other. And the boys as well. So if that's the situation, either the girls have to sit in the first 5 seats, girl, 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 and the boys have to sit in the next 4 seats. Or vice versa. The boys can be in the first 4, and the girls can be in the next 5. But that's kind of the only 2 ways it works, right? That's the only way that all the girls can sit next to each other and all the boys can sit next to each other. So if that's the case, well, in this first situation, there are 5 factorial ways that the girls can be arranged. Because again, we don't care which girl is sitting where. And there are 4 factorial ways the boys can be arranged. And the same thing is going to be true here. There's 5 factorial ways the girls can sit. There's 4 factorial ways the boys can sit. So the total is going to be 2 times 5 factorial times 4 factorial. Okay, let's change it up just a little bit and say, instead of saying the girls and the boys all have to sit next to each other, let's say we want just the boys to sit next to each other. Which might at first glance seem like the same question, but it's not. Because you could either have all the boys to the left, and then girl, 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 girl. But you could also have a girl first, and then 4 boys, and then 4 girls. Or you could have girl, girl, boy, 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 girl, girl, girl. And so on. Girl, 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 4 boys, girl, girl, or 4 girls, 4 boys, and a girl, or finally 5 girls and 4 boys. So there's a long way and a short way of calculating this. You could do each of these. You could say, this one's going to be 4 factorial times 5 factorial. Actually, it's not as hard as you think. So this one's 4 factorial times 5 factorial. This one is the same, actually. There are 4 factorial ways of arranging the 4 boys, and there are 5 factorial ways of arranging the 5 girls in those specific seats. So each one of these 6 ways of having the boys and girls in different seats has 4 factorial times 5 factorial possible arrangements. So what we're going to get here is 6 times 4 factorial times 5 factorial. One way you might see this as there are 1, 2, 3, 4, 5, 6 ways of picking the leftmost seat that a boy can sit in. And then after you've picked where that leftmost boy is sitting, all the other boys are sitting to the right of him. There's 4 factorial ways of arranging them. And then the other 5 girls have to fill the remaining seats. And there are 5 factorial ways that they can fill those remaining seats. So, yeah. If we were going to ask instead about girls instead of boys, so the girls are all next to each other. Let's actually answer the question in the same sort of way we just did. So if there are 1, 2, 3, 4, 5, 6, 7, 8, 9 seats, and there are 5 girls, the leftmost girl could go here, could go here, could go here, could go here, and could go here. Right, but that's the last leftmost seat we could get. Because that seat there are 1, 2, 3, 4, 5 seats, including it that go to the right. So there are 5 choices for where the leftmost girl can sit. And then after we pick where she sits, there are 5 factorial ways of arranging the other girls. And then there are all the girls. And then there's 4 factorial ways of arranging where the 4 boys sit. So same sort of idea. Okay. So let's say we want to look at a similar but different question. And this one definitely does come up typically. So let's say we want to ask how many ways can we seat 5 boys and 3 girls at a round table. And so in the first situation, there's going to be no restrictions. Now, something to consider, and this is typically true when you're talking about a round table. We're not usually identifying kind of how the table is oriented in the room. So like, for example, I wouldn't care if you had, so let's say the boys are boy 1, boy 2, boy 3, boy 4, boy 5. Let's call the girls girl 1, girl 2, and girl 3. So I want to emphasize that this arrangement, which I'll just make very obvious, boy 1 sits here, boy 2 sits here, boy 3 sits here, boy 4 sits here, boy 5 sits here, girl 1, girl 2, girl 3. This arrangement And this arrangement, say boy one's here, boy two's here, boy three is here, boy four is here, boy five is here, girl one, girl two, girl three. These two arrangements are the same. Right? We don't care about where they actually look like from an outside perspective. We just care that if, for example, if you're sitting where boy one sits, for example, that the table looks the same to you. So looking out to boy one's immediate left is boy two, and then there's boy three, and then there's boy four, and then there's boy five across the table from him. To the right, girl one, girl two, and to his immediate right, girl three. And that looks the same from this perspective or from this perspective. Immediate to the left, boy two, then boy three, right? So basically, if you rotate the table and it looks the same, we consider it to be the same. So typically what we do then is to say, well, how do we deal with that? We don't want to overcount things. We usually fix a spot. So we say, okay, we're going to, if there's no restrictions, let's say that boy one, we're going to fix where boy one is seated. And that didn't require a choice. We've just plopped them down at the table. So after boy one is seated, then there are 7 more seats. 1, 2, 3, 4, 5, 6, 7. And since there's no restrictions, there are 7 factorial ways of seating the other 7 people. So, yeah, we're going to get 8 minus 1, which is going to be 7 factorial ways of seating people. And this is considered to be kind of a generally true thing. If you have n people at a table, so n people at a table can be seated in n minus 1 factorial ways. And then we like to ask questions like, well, what if you don't want 2 people sitting next to each other? For example, maybe we know that boy one and girl one really don't like each other. We don't want them to sit next to each other. So we want boy one and girl one not sitting next to each other. So typically we try to deal with them first. So let's fix boy one or girl one. It doesn't matter which one you fix. I'm just fixing boy one because that's the one I wrote first. And then there are 8 seats. There's a seat here, 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 here. Sorry, there's 7 seats total. We pick one of them. Now, for girl one, there are 2 places she can't sit. She can't sit there or there, because that would be next to boy one. So how many choices does girl one have for her seat? I think it's 5, actually. There's 7. Well, there's 8 total, yeah, because there's the seat where boy one is sitting. Yeah, 5. Right, because I took boy one seat and I took away the other 2 seats that girl one can't sit in because they're next to boy one. And then, right, 8 minus 1 minus 2 is 5. So girl one has 5 possible seats to sit in. So let's say we put girl one here. And then after girl one has sat down, then there are 1, 2, 3, 4, 5, 6 seats left that anyone can sit anywhere. So the 6 remaining people, we can arrange them anyway. So there's 6 factorial ways of doing that. So the other 6 have no restrictions. So we're going to get a total of 5 possible choices for girl one times 6 factorial choices or ways of arranging everyone else. Let's do this. We'll do this last one and then we'll call it a day. So what if we want no girls to sit next to each other? I always find this, to be honest, perfectly confusing. Interesting. I've never thought of it that way. That's interesting. So so this is where things are challenging, I will fully admit. We're still going to sit boy one down. And then we're going to make. So basically, you want to have choices about where everyone goes. So I'm going to draw this, but I'm going to leave myself some room. I'm going to say I've got another boy, another boy, another boy, another boy. So the other four boys, they're going to be in some order from left to right around the circle, or some order clockwise around the circle. And if these are the four seats they're in, there's 4 factorial ways of putting them there. Right? Maybe I put boy 2 here, and then 3, and then 4, and then 5, or maybe it's 2, and then 4, and then 5, and then 3. Right? So for boys 2 through 5, there are 4 factorial ways of rearranging them in the 4 seats that they are in. Now, you might ask why I've done it this way. Well, the idea is that I'm trying to make it so that I have space between each of the 5 boys. Now, you might look at this and say, James, you've got too many seats. It's okay. What I'm going to do is say, well, the girls have to sit between 2 boys, right? Otherwise, they will sit next to each other. So each girl has to have a boy on either side of her. And so if I look at this, there are 1, 2, 3, 4, 5 different ways to think about sitting between 2 boys. Essentially, what I've done is I've taken the number of boys and doubled the number of seats. So I've taken my 5 boys, multiplied that by 2 to give me 10 seats, and we're just not going to fill some of the chairs. So there are 5 slots the girls could sit in. How many girls are there? 3. So there are 5 choose 3 ways of seating the 3 girls so that each girl is between 2 boys. For example, maybe I sat them here, here, and here. So that really these 2 boys are sitting next to each other, and these 2 boys are sitting next to each other. There's an empty chair there that we'll just remove from the table. And I feel like Grant left something off on this. What I would say then is there are 3 places we can choose to seat them, but then we also have to multiply that by 3 factorial, because maybe instead of girl 1, girl 2, girl 3, I did girl 1, girl 3, girl 2, or girl 2, girl 1, girl 3, or right? There's 3 factorial ways. So I think our answer here, and it's kind of a complicated question, is 4 factorial ways of arranging the 4 boys that are not boy 1, and then 5 choose 3 ways of picking the 3 seats the girls are going to sit in, and then 3 factorial ways of arranging the 3 girls in those 3 seats. It's not very straightforward. A lot of these questions are not very straightforward. So your job is mostly, it's about the math, but it's also about kind of just figuring out the way to break the problem into digestible, understandable pieces. All right, that's all I've got for today. Next class, we'll be sure to talk about probability. Again, the big thing to know about probability is just that if you want to find the probability of something happening, it's the number of ways it happens divided by the number of total things that can happen. That's the usual deal with probability. An example of that could be like, what's the probability of rolling a 7 if you roll 2 dice? And just the number of ways you can get a 7, which there are 6 ways of getting a 7, divided by the total number of things that can happen, which is 6 times 6, which is 36. So the probability of rolling a 7 is 6 divided by 36. The number of ways you can get a 7 divided by the total number. All right, I'll see you all on Tuesday. Then I'll have a lovely thing. You guys don't have another test, do you? Before the final? Okay, I didn't think so. I just want to make sure. Yeah, because you got a test like a week or 2 ago. Was it last week? Yeah, it was last week. It was last Wednesday, right? Yeah, that's right. Because we didn't have class last Thursday, so I was like, it didn't really make sense. Okay. Cool, well, chapter 12 to the finish. See you all later.
Stop sharing, end it.